and we approaches to the trajectory y of t, and we get this control 5 into our equation into the right hand side, and we obtain inequality equation 6. In this equation we have f and delta f. F we know, y we know, delta f is corresponding changes in the right hand side, and we don't know exactly, but we know that that is small enough, sufficiently small, and we have to analyze second order equation. Next, please. Okay, well, if we denote that as difference x and y, we obtain the second order equation 7 for the difference of x of t and y of t, and of course, no corresponding equalities in the right in the initial condition, and we have to obtain stability of our equation 7. It means that if delta f is small enough, we have to obtain that z is solution z is small enough. And that is a classical problem of stability with respect to right hand side. We have to obtain the solution of homogeneous equation when here is 0 tends to 0 as exponent. As exponent here. And that is a problem of exponential stability. It is known that exponential stability is equivalent to stability with respect to right hand side. Next, please. Absolutely the same equation for analysis we obtain in quite different problem of stabilizing the rolling of a ship by the activated tanks method, in which ballast water is pumped from the one position to another. This model was described in the book of Minorski, American mathematician. Originally, he's from Poland. And what is the idea? We have a vertical line matched, and waves from sides starts the corresponding rolling moving of the ship, and we have guarantee that the angle phi is smaller than corresponding phi 0. If they're greater than corresponding phi 0, our ship sinks. And we have a corresponding equipment in order to stabilize rolling of the ship. Next, please. The other problem model of robot rider there, and I take it from the book of Fomin Fradkov-Yakubovich, and we obtain the second order delay differential equation. Why in all these models we have delay? We have delay in order to obtain signal from the object and to react on this signal. And that is why we don't, instead of ordinary differential equation, we have to need delay differential equation. And delay is very essential. In almost all results, delay should be small enough. Or the next, please. Next, please. Next, please. The same problem is in the area of artillery gun after shooting. What we have to achieve here? We want to achieve that stabilization will be very quickly. And then our artillery gun is ready for next shooting. And here is a model like in rolling motion of the ship. Second order differential equation for the angle. Next, please. Yes, and of course, in all this problem, we have to consider system of three equations for x, y, and z, but we limit ourselves by only one of the equation, scalar equation of the second order. Equation 1,5 with constant coefficients p and tau. Equation with variable coefficients and delays p of t, and the equation we have many terms with variable delays. Next, please. The idea of stabilization but feedback control was realized in various applications, and I note only several examples of these realizations. Next, please. Our approach to stability is based on oscillation, on non-oscillation properties of solution. The concept of stability was proposed in the following two books of my supervisor, Professor Aspele from Perm. Next, please. Okay, various aspects of oscillation and asymptotic behavior of second order delay equation were considered in the known monographs. Now, of course, of Mishkis, of course, Norkin, Hungary mathematician Dieri, and American mathematician Madras, Koplatadze from Georgia, American mathematician in India, and China's mathematicians, with initial function phi. Next, please. And it is possible to write general solution in this form. And what we see, x1, x2 is two solution of homogeneous equation, non-dependent, and C of Ts is a solution of the homogeneous equation for every fixed S. And it is absolutely the same definition as in the case of ordinary differential equation. Behavior of solution is determined properties of boundary value problems and stability of ordinary differential equation, of differential equation with delay, like in the case of ordinary differential equation. Next, please. Yes, and but now let us consider delay differential equation. What are difficulties in its analysis? And I'd like to compare properties of delay equation with properties of ordinary differential equation. Consider, for example, this equation with non-positive coefficients. If we consider an ordinary equation where tau of t is 0, what do we know? And even constant coefficients, we know that we have two real roots of differential of characteristic equation, and we see that solution of this equation can have only one zero. What we see here, we see that solution of this equation, of equation 1, 8, is the following function, x of t, and it change its sign twice, which this fact is impossible for ordinary differential equation. Please, next one. And in the case of this equation with tau of t of this sort, we have a solution which has infinite number of zeros, oscillating solution. It is absolutely impossible for ordinary differential equation if tau of t is 0. We have only two roots of characteristic equation 1 and -1, and it is impossible to achieve oscillation. But in the same time, we see that if we take initial condition of the following sort, y0 is 0, derivative of y at 0 is positive, we obtain that another solution is non-oscillating, another solution is increasing and tends to infinity. When a solution has so absolutely different properties, it seems impossible to obtain something about stability. They are so different. Behavior can be so different, and it is impossible to obtain corresponding similarity in the behavior, stability of properties. Next, please. Okay, and there are many results on delay equation and analysis when there exists solution tending to infinity, where there exists oscillating solution, and where solution and its derivatives tends to 0 when t tends to infinity. I can know the following: Skubachevsky, of course, Kaplatadze. Next, please. In the United States and China, in India, we have many other results with very similar conclusions, where there exists a solution tending to 0, that is analog of results that one of the roots of characteristic equation is real and negative. And so, next, please. In the case of positive P, we have many results about distribution of zeros, about Sturm theorem, about separation of zeros, and so on. I can note the following papers in this direction. Next, please. And what is important here? For oscillating properties in the end of 70s, it was clear that equation with delay inherits oscillation properties of ordinary differential equation. For Holland mathematician Brans obtained it that for every non-negative P of t and bounded delay, equation 1,6 is oscillatory. It means that all solution of this equation oscillating if and only if ordinary differential equation is oscillatory. But for asymptotic properties, we have something else. Mishkitz proved that for every positive constants, p and tau, we have unbounded solution for equation 1.5. For every positive constant, it is strange that for a case tau is 0, we have general solution of a homogeneous equation as a linear combination of sine and cosine, all solution abounded. But every positive delay induces existence of unbounded solution. Next, please. For variable coefficients, the first results of the sort were obtained in the following my paper. And what if coefficients are variable, what we have to require, if tau of t is greater than corresponding positive epsilon and coefficient p of t is greater than corresponding epsilon, then there exists unbounded solution of equation 1 to equation 1.6. Next, please. Okay, and if epsilon is 0, the null solution of the following equation are bounded. You can see that delays are very small. Delays tend to 0 when t tends to infinite. Here, in the first, in the second, and in the third equation. But appearance of delays changes absolutely properties of asymptotic properties of these equations. We see that all of them have unbounded solution. Also, in the case of epsilon to 0, all solutions are bounded. Next, please. Necessary and sufficient condition for bounded, so full solution of equation of is the following. If p is bounded, p of t is bounded in 1.6, then integral of integral is bounded. Integral of delay is bounded. We have that solution is bounded if and only if. And what we can say, we can see that delay control could not stabilize our motion, for example, in the problem of motion of single mass point. Why? From mechanical point of view, it is clear. Next, please. Next, please. And I explained. Next, please. Next, please. And what we need to know from the theory of delay differential equation. Our equation is of the second order, is uniform exponentially stable if there exists a positive constant n and alpha, such that the solution of this second order delay differential equation satisfies the estimates 210. And as a definition, we say that Cauchy function CTS, Cauchy function is the kernel of integral representation of solution, satisfies the exponential exponent if there exists positive n and alpha, such that there is a following estimate for CTS. From the theory of algebra, it is known that for equation with bounded delays, these two facts are equivalent. Uniform exponential stability and exponential estimate to 11 of the Cauchy function. We have to obtain this estimate. Next, please. We'll demonstrate that also the ordinary differential equation 3-1 can be oscillating and asymptotically unstable, but the delay equation 2-3 and the corresponding condition on the coefficients p it and delays tau it is non-oscillation and exponentially stable. What is important idea? Important idea is that we don't assume that coefficients are all non-negative. Coefficient can be positive and can be negative. Should be positive and should be negative, maybe more exactly. Next, please. Let us consider the following simple example. We have only two terms here, with positive coefficient and with negative. And we denote that if we set star below, we have it is S infimum, that is S supremum of the coefficients. Next, please. And we obtain the following facts. Assume that delay of positive is less than delay of negative, and positive term is greater than absolute value of negative. Yes, greater than b of t. And what we have to require? We have to require that tau theta, difference of delay, theta minus tau is sufficiently small, such that condition 3.6 is fulfilled, and the difference between the coefficients is also sufficiently small. It should be less that difference of delays in a corresponding function. Yeah. And what we can say? We can say that the Cauchy function is positive, and if there exists such positive epsilon that a minus b greater than this epsilon. Next, please. Then we have exponential estimate of CTS. It means that we have uniformly exponential stability of our delay equation. And it is important that the integral of CTS is less than this 1 divided by epsilon. Okay, and next, please. And what we can do if delay are constant. If delay are constant, and we have a very simple assertion 3.11, which gives us smallness of difference of delay. And here we have a very small, simple condition for difference of the coefficients. Okay, next one. And consider the unstable equation. No, why equation is unstable? If delay is positive tau, positive constant, we have, I demonstrate that our solution, our equation have unbounded solution. And of course, here the case of oscillation solution, and we have house in solutions behavior. To stabilize solution of this equation to the given trajectory y of t, we take control in the form of three setting. A possible algorithm to construct this stabilizing control is clear now. First of all, we choose delay theta close to tau, such that condition on delays is satisfied, and B should be close to A, such the condition 310 is fulfilled. And we obtain stabilization of this equation. Next, please. Okay, and no, in the case that A and B are also constant, we can change, for example, theta such that this equality is fulfilled, and we obtain inequality for the difference A minus B. Next, please. This situation is very difficult for analysis. A of t tends to infinity. No, of course, we have unstable situation. This equation have unbounded solution, and we can take u of t in the form 3 setting, the same form like in previous example, and we can achieve that our equation will be stable. Now, for example, if we take instead of a of t, t, h a t minus tau, of course this equation is unstable. But what we can take instead of b of t, instead of b of t, we take t minus delta, and instead of theta of t, tau plus gamma divided by t. And stabilization can be achieved by the control 3 setting with parameters satisfying the inequality 318. Even the case when a of t changes to infinity can be stabilized by our control of the form 3 setting. Okay, next, please. We have also another theorem about stability. Here, we demonstrate here other conditions, and when we can guarantee that solution are positive, CTS is positive, and CTS satisfies exponential stability. Next, please. That is absolutely similar facts. Next, please. Next, please. Okay, and what is important here? Difference between delays should be small enough. That is an important assumption. If we take, for example, equation of this sort, and theta greater than pi, then in the triangle, its Cauchy functions is less than 1. It means that this condition could not be fulfilled. And this condition in our theorem about smallness of delay is essential. Next, please. And if we consider now general type of this equation, but what I want that we have even non-homogeneous equation of 5.1 and homogeneous 5.2. Next, please. And let us assume that coefficients are positive, negative, positive, negative, positive, negative. And delays of corresponding positive is less than the delay of corresponding negative. That's all we need. And the Cauchy function of the first order equation, 5, 3, is positive. No, this assumption seems very difficult and unclear, but we have simple inequalities which gives us this fact. Next, please. And the following assertions are equivalent. Assertions are there are three assertions, three equivalent assertions. V, there exists corresponding function, V satisfying corresponding inequality. There exists a bounded absolutely continuous function U satisfying corresponding inequalities. And the part 3 is non-negative Cauchy function CTS. 1 and 2, assertion 1 and 2 are entrances to this fact, and we find V and U of satisfying for 5, 4 for V and 5, 5 for U. And if we find this function, we can say about positivity of CTS. Next, please. We can, and a very difficult condition we have, but actually we have only to need the following simple inequality in order to obtain sufficient condition when the second condition in this theorem concerning first order equation is fulfilled. Okay, next, please. Maybe next, please. That is corresponding generalization. That is corresponding technique. Next, please. And we can obtain the following. Assume that coefficients are positive, negative, positive, negative. B, that is operator, we know it, and we can verify this inequality. And what we have, there exists alpha such that inequality 5, 20 is fulfilled. Then the Cauchy function is non-negative, and if difference when positive and negative greater than corresponding epsilon, then exponential stability. What we see here, if pi of t all are non-negative, we could not obtain this fact. Why can the first term in 520 is of course non-negative, the second is non-negative, and we could not obtain this fact. We can obtain this inequality 520 is fulfilled only in the case when there are negative coefficients among pi of t. Next, please. Okay, that I explained that difference of coefficients should be positive, and we have that C of Ts of our equation satisfy exponential exponent, and we have the exponent of integral of CTS. Next, please. Next, please. Okay, and why the condition that difference between positive and negative coefficient should be greater than epsilon? No, let us consider this equation, and here epsilon is 0, coefficients 1 and 1. And what we see is that constant is solution of this equation, and we don't have exponential tending to zero. Consider now the equation of this sort. We have this part we have in previous theorem, and we add corresponding terms. And what we can have? Okay. And next, please. And consider now this equation, homogeneous equation. Next, please. And we have assertion as if Q is negative, we have that the Cauchy function is positive if Cauchy all condition of previous theorem is fulfilled, and we have condition if we have condition 564, we have also exponential stability. That's all I want to explain you today. Thank you very much for your attention. Question, please.
So, Alexander, you would improve the results. I mean, generalize the results to neutral differential equations.
I don't hear exactly, but the reason is in all real technological models, we have delay. We have delay in receiving signal and delay in sending our control. And that is why delay appear very naturally in all these models, and we have to analyze the influence of this delay. And you see that in many cases, delay help us to stabilize the process. And before our works many years ago, delay was considered as a negative factor for stabilization. But starting with this paper, and then in our monograph with Berezansky and Kaplatadze, we get many results when delay help to stabilize the process.
What I remember, you and one of your PhD students have done some mathematical models on some mechanical problem. I think human body problem.
Yes, you're right. Yes.
Yes,
we see many examples in mechanical problems, model of human balancing.
Yeah, human balancing.
And we have many examples in medical problems. In medical problem, delay is also very essential. We know that we need the time when our medical to start to influence on the
many models related to cancer patients and so on. You have obtained, I think. In the seminar I have seen. That's why I'm asking the result what you have presented today, the lectures you have delivered. Have you generalized them to neutral equations? Can the result be applied to the models what you have obtained for a human body, human balance?
Yes, of course, and of course in all development of technical prothesis, of so-called clever prothesis, the concept is to consider an invalid as a part of robots, and of course it is very essential. Um,
So participant, now we will start our next session after 2 or 3 minutes.
Hello.
Yes, sir.
Hello.
So, hello.
We hear you, sir.
We can hear you, sir.
Hello.
Okay. Yeah. Can you hear me? Yeah. Thank you.
Yes, sir. Yes, sir.
Okay. Okay.
So now we are going to start our session number 5. So it is a great pleasure for us to invite our next speaker, Professor Vetrivel sir, who is going to talk to us about convex optimization. Before we start this session, first of all, a warm welcome to Professor Vetrivel sir in this mathematics seminar. in science and engineering applications. Also, on the behalf of Department of Mathematics, VIT Mesra, I want to thank you, sir, that you have accepted our invitation as a speaker. Now, ladies and gentlemen, I would like to give a small introduction of our speaker, Vetrivel, sir. So, Professor Vetrivel, sir, currently has a position of head and professor in the Department of Mathematics at Indian Institute of Technology, Madras. Sir is expert in many fields of mathematics, and his broad area of research are nonlinear analytics, variational inequalities, optimization, and fixed point theory. Sir has published a good number of the research papers in the reputed journal. Sir has supervised till now 12 students. Sir is also the reviewer in several reputed journals. Now, if I say more about him, probably the whole session will be less. So I end your introduction, sir, with this word, and I hope all the participants will enjoy the entire session, and definitely this session will be very, very helpful for all of us. So now, with this word, I over to you, Mike, too, sir, and I request you, sir, to start your talk, sir. So thank you very much.
Just 1 second, sir. I need all the participants whose video is on, kindly close it. All the participants whose video is on, kindly close it. Rush Singh, RASH, Rush Singh, kindly switch off your video. That will help us a better live stream. Sir, you can start. Thank you, sir.
Yeah. Just 1 sec. Yeah, 1 sec. Thank you very much. Thank you, Dr. Seshadev for giving me this opportunity, and also continuously I had a conversation with Dr. Piyush. Thanks for inviting me in your seminar on mathematics, SEA, Science Engineering Applications. So I'm sure I'll be able to contribute something. That is, it will motivate some people, because this is the topic. I'm not going to talk anything new here in this. I know very well that many people are belonging to a different area of research. So my focus today, because whenever I get new student, I give this talk to the people. And in fact, one of my students got very excited about this topic. And then he started working on that field, and he completed his PhD, and then he got a lot of postdoc positions, and then he became one of the authorities in the topic, the convex optimization. And he has written a couple of books on that. The third book has come. He is a professor and head. He was now not a head in IIT Kanpur. His name is Jaydeep Datta. Afterwards, I used to always give this talk wherever I meet the new people. This talk is based on this book called Lectures on Convex Optimization. Okay, lectures on convex by. I will give you the reference in my presentation. This is the book published in 2018. It's a second edition book. First edition appeared in 2004. And then with a lot of modern components are included in this. For example, because the convex optimization is very most emerging always because of its application in machine learning algorithms. Wherever if you go to any machine learning algorithm, topic, if you open, one of the important tools is convex optimization. So my focus is not on machine learning, but only the convex optimization, the basics of convex optimization. With that brief introduction, I share a file. Yes. So I will give the reference. There is a reference, is a more elaborated one. But here I just condensed material from this book. Okay, I cannot give in a 1 hour presentation. I cannot give the full information, but anyway, I will try to convey the what is basically in converse optimization is happening. Hope you are able to see this file. Anything not clear, please let me know immediately. Like the link or the things are not visible, please let me know. Okay. Yeah. So thanks for the nice introduction anyway. See, we are interested in generally optimization problem. When I take optimization problem, the problem is with the existence, with the solution. The existence of the solution or how to compute the solution, it is always a problematic. Okay, it's not easily solvable in general. Okay, some problems are solvable. In analysis, in real analysis, when you study it, if there is a continuous function defined on a compact set, then it attains the minimum or maximum. Okay, minimum and the maximum it attains in the compact set. That we know. Okay. So therefore, the domain has to be compact. Critical point or to get the solution, we cannot do. So generally, so this is our. We want to develop. If this is my problem, x below minimum of f of minimize f of x. We call it minimize f of x. And the x bar is a local minimizer. Local minimizer means only in the neighborhood it should satisfy that inequality. F of x bar is less than or equal to f of x. So such a problem is called a constraint program. So it is not necessary that the gradient is equal to 0. So we call this program is a convex program. We call it in optimization terminology literature. We call it, the problem is called this minimization problem is called a program, minimization program, okay, like linear program. That is the over literature, okay, in terminology. Minimize. So here convex means my set of C also has to be convex. F also should be a convex function. Convex set means we know any 2 points line joining should be inside the set C. Function is convex means you know that in calculus we must have studied that f of lambda x plus 1 minus lambda y is less than or equal to lambda times f of x plus 1 minus times f of y. That means that the line joining between any two, the graph lies between the line segment joining any 2 points x f x and y f y. The curve lies below. That's what this inequality. This is purely algebraic. Okay. In case I know that the function is differentiable, this inequality, the definition of convexity, there is another dual representation. In the case of differentiability, if f is convex, then we have this inequality satisfying. F is convex if and only if. F is a convex function if and only if this f of x is greater. That means that it says this inequality says that the tangent at any point to the convex graph will be lying below the curve. That means the right hand side is simply the distance between x and this straight line, this tangent line. Whereas f of x is the distance between x and the corresponding point on the curve. Okay, so therefore f of x is greater than or equal to this. So that means that the tangent line always lies below the, if the function is differentiable. Otherwise, I no point in using this inequality. So these are the two. This is the definition of convexity. Here itself we can see that if the gradient is 0, then we can say that fx is greater than or equal to f of y for all x. So therefore we can say the minimum is satisfied. So the examples of convex functions, we can give a lot of examples. For example, in any linear function or affine function is a convex function. Therefore, the whole linear program is a convex program. So in optimization theory, the distinction is not between linearity and non-linearity. The distinction is between the convexity and non-convexity. Because every linear program is a convex program. But in general, an optimization problem need not be a convex program. Only because all the functions involved should be convex. The domain should be the set C is called the feasible region. The set C is called the feasible region. So F should be convex. This is called feasible set. Okay, the constraint set. Both should be convex. The function should be convex. The set C also should be convex. So sometimes what happens is if one of them is not satisfied, then it is called a non-convex program. But in the only problem is non-convex program. Whenever we deal with a non-convex program, what we do is we convexify, like how we give a linear approximation to some nonlinear function. The same way here, the non-convex program is approximated by a convex program. Because convex program, we can at least expect, we can compute the solution. There are some efficient algorithms available. Okay. So these are some examples of convex functions. A transpose x plus b, a linear function. And also the quadratic function is a convex function. Quadratic function means you know that A is a symmetric matrix. B is a Rn vector and C is a constant. And f of x is this quadratic term. So this is again a convex function. Therefore, the quadratic programs are also a convex program. And in one dimension, we can always say e power alpha x for any alpha is a convex function. And x power alpha for alpha greater than or equal to 1 or alpha negative. This is a convex function. And also mod x power p greater than or equal to 1 also is a convex function. And in the case of n variable, I can replace the mod by norm x. And again in one variable, I can say fx is equal to minus ln x is a x positive is a convex function, and x ln x positive and equal to 0 x is equal to 0. That is also a convex function. And more than that, this ln of in the n variable case, f of x is equal to, where I say when we write x is equal to x1 x2 xn, then f of x is equal to ln of e power x1 plus e to the power xn is a convex function. And sum of convex functions is a convex function. And max of the max function, that is, you take any convex function and you take the max of that, that is again a convex function. Though we lose the smoothness of the function, again still it is a convex function. And this sum of convex functions, not only sum but also the weighted sum, is also again a convex function. So a lot of because in many applications we deal with such convex functions. One simple example of a convex optimization problem. So x minus 3 whole square, because this is because x square is a convex function. Therefore, x minus 3 whole square is a convex function, and this is a convex set minus infinity to 2. So simply it's a parabola x minus 3 with the vertex at the point 3, and the region is the feasible region is only minus infinity to 2. Therefore, the minimum is attained at the end point 2. So therefore, x bar equal to 2 is a solution. We know that. And another advantage of the convex optimization is, if I try to find the local solution, local minimizer, it also becomes a global minimizer. That is the advantage of the convex program, convex optimization problem. Both are synonymous, convex program or convex optimization problem. Generally, the convex set, the constraint set in the actual application side, okay, will be of this pattern. The constraint set C is generally given by some inequalities or equalities, some set of inequalities and some set of equalities. So where Gi and Hj are function from Rn to R. Okay, so we have, so this is the more, so this such a set C is called a, if I want to minimize some function f of x, then that f of x is called the objective function, and this Gi, Hj are called constraint functions. And this set C is called the feasible region, or simply the primal feasible region, the primal problem, okay, like our linear programming, the same terminology here too. So a convex optimization problem is minimize fx subject to these conditions. That's all, because any x satisfying these two equalities, inequalities and equalities is called a feasible point. Okay, the set, if I collect all the x such that x satisfying these inequalities is called our usual notation C. So here we assume that the objective function gradient algorithm, because we know that when we want to minimize an unconstrained program, we have studied in numerical methods a lot of gradient algorithms, conjugate gradient method, all that. The same thing here, the gradient algorithm I use for this optimization program. So our inputs are F and C. If I fix the iteration, T or T iterations, and I select the step size eta T, generally we put the eta T to be 1 by T. What I do is in between we compute one more point. I start with I initialize the x1 point, and then I x tilde T plus 1 is xt, the usual gradient. Okay, I proceed along with that gradient, the negative gradient direction, because negative gradient direction is the direction of maximal decrease. Okay, so therefore xt minus eta T gradient, I proceed in that, and then what I do is this x tilde T plus 1 can go outside C, because our solution has to be inside the C, the feasible region. It should not go outside C. So this is my set C. The geometry of the C sometimes will be very complicated. Okay. What happens is, but only the thing is, we know that here sometimes, since for a convex program in general, the C is at least a convex set. Okay. General optimization problem, the feasible region will be very, very complicated geometry. So what I do in the next step is, after x tilde T plus 1, I project it in the set C. C is a convex set. In fact, C will be if I assume some smooth conditions on the GIs, then I can say that the C is a closed set, and hence I can find a unique xt plus 1, the projection point, the point which is nearest to x tilde T plus 1, because I don't want that iteration to go outside the set C. So I just, if it goes, in the next step, I project it inside the C, xt plus 1. So this PC is called the projection map, projection on the set C. I project the x tilde T plus 1. So this is how I compute the xt plus 1, and then I take the output, this xt plus 1. X capital T plus 1, that is the final iteration. Whether, so as I said, the algorithm will converge. There is a proof that algorithm converges to the global minimizer, because I told you this local minimizer is a global minimizer in this case, because convex program. The difficulty in this case is how to compute the projection point, so that's the only difficulty lying here. So that is why I said it's not a very effective method. Okay, now, so there are different algorithms. I'm not going into the algorithm side. So let us take P star with objective value of the primal problem. Primal problem means, what I mean is minimize fx subject to x belonging to C. The C is given by set of constraints, the equality constraints, inequality constraints. And P star is essentially this, the infimum of the f of x. In general, P star will not be achieved, because we know that C is not a convex set. Suppose if C is some quadrant or one ortho, then we cannot expect the infimum. We cannot find a point x bar such that f of x bar is equal to P star. So that is the problem. Okay, because our set C is generally maybe an unbounded set. So you cannot expect a point x bar. So in that case, what to do? Okay, so that's a difficulty we face in optimization. Now, what I do is I find a set of constants lambda 1, lambda. I take lambda 1, lambda 2, lambda m from Rn, that is a m tuple, and a k tuple, nu 1, nu 2, nu k. And then I form this combination, fx, the objective function, plus lambda I gix, plus sigma nu j hjx. Okay. So see, this is called Lagrangian function. You know that in calculus, when we studied only with the equality constraints, we have studied this Lagrangian function. So this lambda j lambda I nu j are called Lagrange multipliers. Sometimes they are called KKT multipliers. KKT means Karush-Kunteker multipliers. So this is my lambda. The lambda belonging to Rm and the nu belonging to Rk. Now, once I have this Lagrangian function for a given primal problem, I set this phi lambda nu. For every lambda nu, I minimize this L function, this Lagrangian function over the x in R, and this is an unconstrained problem. Okay, unconstrained problem, we have a lot of algorithm to solve. So I just solve this because in calculus itself, I can take the gradient and solve the system of equations. Once I have this for every given lambda nu, if I am able to find this infimum, then the value is denoted by this phi lambda nu. So this phi is called the dual function. So for any primal problem, I can find the dual function. Why I am finding dual function, that we will see now. Once I get the dual function, I maximize it for different. I just because only for the lambda I has to be non-negative. Nu can be anything. I maximize over this lambda for all lambda. Okay. For lambda greater than or equal to 0. So I consider this new problem. You remember this D. This is very important point. This is a deep. This is for any primal problem. One can construct the problem D. This D is called dual optimization problem. Remember, the important points are here. This phi function. This phi function is always it's a concave function. One can prove that it is a concave means minus of that function is convex. So minus of the minimum is equal to the maximum of the minus of the function, negative of the function. So therefore, this problem D max of the concave function. That means that it is a convex program. So it doesn't matter what your P is. Initially we started with the P simply. Okay. We have a problem P. The problem P is simply minimize fx subject to some constraints. So therefore, I have a primal feasible region and all that. I assume that the primal feasible region is non-empty. And then I set this L. Once I know this, once I write this L, I take the minimum. I take the infimum over all x in this unconstrained problem I solve and set this phi function. It's called the dual function. Once I find, I consider this maximization problem, which turns out to be always a convex program. So even if my primal problem is not a convex program, my dual problem will be a convex program. Therefore, because once I know convex program, then it is easy to solve for me. Okay. The things are better when I face the convex optimization problem. And that's what I mentioned here. Even if P is not convex, D is always a convex program. So once I have a convex program, for this the dual program, I consider the feasible region. What is my feasible region here? All the lambda I greater than or equal to. Nu can be anything. Okay. Nu can be anything. So lambda nu. This is the feasible region of the dual problem. Okay. Now let us find the D star, the objective value of D. Let us say P star is the objective value of the primal problem. Okay. In linear programming, we have studied that the primal objective value is the same as the dual objective value. Okay. Here, in general, this is not the case in the case of general optimization problem. There is a duality gap. So now D star is defined. What is D star? As by definition, the maximum, because it's a solution of the dual problem. The supremum of phi of lambda nu, where lambda nu belonging to the feasible region. Okay. So if I write down this phi of lambda nu, let us take some primal feasible point. Let's say x or x bar or simply x. be a primal feasible point. And then I consider this phi of lambda nu. What is phi of lambda nu? By definition, it is infimum of the Lagrangian. Okay, it is the infimum is Lagrange. The infimum is taken over the first variable x or x prime I have written. Okay, since I already used the x here, I have put x prime. So this, by definition of infimum, this is less than or equal to L of x lambda mu. What is x? X is the feasible point, a sample feasible point. So L of x by x lambda nu, by definition, it is f of x plus sigma lambda I j of x plus nu j of x. Since x is a feasible point, the last term, the third term will disappear. And this is not because lambda is greater than or equal to 0, gi of x is less than or equal to 0. So that's what we have the inequality. So therefore, this is less than or equal to 0. This is the third term disappears. Therefore, it is less than or equal to f of x. So what we have is phi of lambda nu. If I take any x, a primal feasible point, then phi